Okay, so we haven't really done a ton of forces of vector quantity stuff yet. We did inclined planes yesterday, and certainly there was some tail to head drawing inside of the plane, but it's always the same diagram, FG and F normal. Okay, what we're going to look at today is more of the, all right, these are two forces that are definitely going different directions. What's the net force going to look like? Tail to head drawings, okay, doing X and Y, all that kind of stuff. Now you guys are good at that. You guys know how to draw the vector diagrams, you know how to calculate vector components. So the only thing that changes here is that now it's force and not displacement. Okay? And everything else is the same, okay? And you'll get the net force as your resultants. All right, so I'm going to have you copy that example down, okay? And then we'll kind of work through it together, and then we'll look at a few problems related to that. Okay, so we have a 50-kilogram box being pulled along a level, frictionless floor by two forces. Actually, I'm not even going to draw that line there. That's not going to make sense. So we're actually going to be drawing this free body diagram as though we're getting a bird's eye view of it. So we're looking down on it from above. Okay, so we'll have the box, okay, which is 50 kilograms, and it's being pushed 35 degrees north of east with 150 newtons. All right, so here's east, okay, and we're looking at 35 degrees, so something like that maybe, and 35 degrees, 150 newtons. Okay, the second force is directed 10 degrees south of east and has a magnitude of 115 newtons. All right, so it's shorter and it's south and it's only 10 degrees, so maybe something like that, 10 degrees, okay, and it's 110 or 115. All right, calculate the acceleration of the box. So it's on a frictionless floor. Okay, those are the only two forces acting. Which way is the box going to go? Like, is it going to be a little bit north of east or a little bit south of east? A little bit north. Probably a little bit north of east. It's a bigger force. It's a bigger angle. I think it's going to end up being a little bit north of east. Okay, and it's always good to kind of visualize that first. So that's my free body diagram. What do I need to draw now? Right, I got to draw vectors tail to head, get my triangles, okay, so that I can get the vector sum of these two forces. All right, so my first force, okay, is the 35 degree one, 150 newtons, okay, 35 degrees, this will be X, this will be Y, okay, and then move my free body diagram over a little bit so it's not in the way. And then I'm going to change colors and go, here's east again. I'm going to go 10 degrees south of east. That'll be Y. That'll be X. That's 115 newtons. Right? And then that means my resultant is going to go like that. So that'll be theta. My resultant will be the net force because it will be the vector sum of the two forces I'm working with there. This will be X and this will be Y. Okay, everybody all right with that? Okay. If I'd have put meters on the end of those two numbers, you'd have drawn that like no problem. You probably drew it no problem anyway. Okay. All right, so now that we've got our vector diagram, now we want to calculate all of our components. Okay, so we'll start with the blue line. Okay, blue X is going to be the cos of 35 times 150. Okay, so 122.873. Newtons east. Okay, the Y component for the blue triangle, sine of 35 times 150. Okay, so 86.036 newtons north. Okay, then I gotta do the same thing for my purple triangle. Okay, so purple x is gonna be the cos of 10 times 115. Okay, so 113.25 newtons east. Okay, my y component is the opposite side, so sine of 10 times 115. Okay, so we're looking at 19.970 newtons south. Okay, can I find the x and y components of my net force? All right, so red x, okay, is going to be 113.25 plus 122.873 because they're both north.
They're both east or north?
Or sorry, east. Yeah, they're both east, sorry. Good catch, Tony. All right, so 113 plus. Someone's got to watch out for me because I'm old. Okay, 236.126 newtons east, because that's the way it's actually going. Okay, and then y, we've got one that's north and one that's south, so these ones will have to be subtracted. So we will have our 86.036 minus 19.970. All right, so we're looking at 66.067. Newtons north. All right, so now I know these two sides here. Okay, 66.06. Okay, this one's 236.126. So just looking at those numbers, my scale is not great. Okay, my theta is probably a bit big, but oh well. It still generally represents what's going on here. Okay, can I get my net force now? How? I use the Greek geek, right? Okay, I go to Pythagorean theorem, right? And I'll get F net, so that'll be the square root of 236 squared plus 66 squared, obviously with all the decimals in place. Okay, so 245.194 newtons is the magnitude of my net force. I also need to get theta, which the way I drew that triangle, okay, y was the opposite side, so the 66 over the 236. All right, so we're looking at 15 degrees. Well, that's not terrible. It's a little bit big, but it's not terrible. Okay, 15.6 degrees. For me, that's north of east. Okay, now, what did the question want? Okay, how do I get that?
Just do F net divided by mass.
Right, F net divided by mass. Use m times a. I mean, I just did all this vector sum of all forces stuff for the last like 6 minutes. Okay, so now I might as well get acceleration using m times a. All right, so F net will be our 245, okay, with all the decimals divided by our mass, which was 50 kilograms, I believe. Yep, 50. Okay, so my acceleration is going to be, and we only had 2 sig digs, right?
Yeah.
Yeah. Okay, is gonna be 4.9 meters per second squared at, well, actually at 16 degrees. That's 2 sig Gs. Okay, at 16 degrees north of east. Okay, so that'll be my final answer there. Okay, 4.9 meters per second squared at 16 degrees north of east. Okay, so it's a vector addition question with an m times a tacked on to the end of it. Okay, nothing you guys can't handle. Okay, we just haven't done one because they're tedious. As all vector addition is tedious. You gotta find why. Yeah, you do. Okay, but as long as we know how to do that, the extra step on the end is not something that's going to be challenging. So these are probably not ones that are really going to make you think very much because you know how to do them. It's the ones with strange contexts like we've been working on over the last few days. Okay, you know, like a person standing on a bathroom scale in an elevator for some reason. Okay, those ones are sometimes bigger thinkers, even though they got less work to do. Okay? Sometimes it's nice to just have one that's got work we know how to do, so we can just do it. Okay, see what we remember about inclined planes from yesterday. And I said this is sometimes something I do with an inclined plane question. It's a 340 Newton box, not kilograms, newtons. What property of the box would be in newtons? The weight, exactly. Okay, so that 340 newtons is the force of gravity acting on the box. So you can get the mass, okay? Well, you might. No, I don't think you will actually on this one. But you sometimes do. If it asks you to calculate the acceleration, then you would have to go 340 over 9.81 to get the mass. For this question, I don't think you're going to need it.
So to get the mass, you would just divide by 9.81.
Just divide by 9.81, yeah. Okay, I'll give you a couple minutes on that one. All right, what are the key words in this question? Constant velocity, okay? Anytime you see those, it's giving you a big juicy hint, okay? That the net force is 0, and that's always helpful, okay? So, we have our 30-degree incline. We have this box with a weight of 340 newtons. Okay, so that tells us that this side of that triangle is 340 newtons. Okay, this side's F normal, but I'm not going to need it. I'm going to need F parallel though. Okay, there's really not a situation on an inclined plane where you wouldn't need that force. Okay, so I got my 30 degrees here. Okay, so since F parallel is the opposite side, I would go sine of 30 times the hypotenuse, which was 340, which should give me 170 newtons as my F parallel. Okay, so I know that one of the forces acting downwards is 170 newtons. Then they tell me the applied force up the ramp is 200 newtons. Okay, what's the force of friction? All right, since the box is going up the ramp, even at a constant velocity, it's still going up the ramp. Which way is friction acting? Down the ramp. It's antagonistic. It always works against you. Okay, so force of friction goes here. Now, since it's moving at a constant velocity and F net equals 0, that means that the force of friction plus F parallel plus the applied force add up to 0. In other words, F parallel plus X equals 200. Right? I have to have 200 newtons down the ramp if I've got 200 newtons acting up the ramp and I want my net force to be 0. Would you agree? Okay, so how big is friction? 30 newtons. Yeah, that's all there is to it. Okay, so we had to do, two calculations. Okay, we had to calculate F parallel, and then this math we could pretty much do in our head. Okay, 200 minus 170 gives us that force of friction of 30 newtons. I once had a question like that on a unit exam.
I have not since put a question like that on a unit exam. Why? Because it tricked a whole bunch of people. Yeah, it actually went really poorly. Because people overthought it. Okay, they looked at it and went, what? That can't be right. That's too easy. And I thought, maybe that was mean. Maybe it was mean to put an easy one on there. Okay, because people just figured, Coder's a jerk, so he's gonna put something hard on there. Like, they were kind of right. It ended up being a hard question when it really shouldn't have been. And people just didn't think it could have been as straightforward as it was. Okay, sometimes they are. We've done a ton of questions that really didn't involve a lot of math. Okay? They just involve some thinking. All right, questions on that inclined plane? Okay. All right, try this one. Another inclined plane question. Okay. So you're sledding down a hill. Okay, it's a 25-degree angle. Friction is resisting with 150 newtons, and the child has a mass of 50 kilograms. What's their acceleration? It's a big kid. It's like 110 pounds. Big kid. You guys are kids. All right, so on an inclined plane, okay, we draw our little triangle here. So we got our 50-kilogram child. Okay, we know that this is going to be FG. Okay, this is going to be F normal. Right, and then that's going to produce F parallel. All right. Now the confusion that I'm seeing, and I see it, most of the time when we first start out with inclined planes, is that when people go to calculate the net force, and we had 150 newtons worth of friction up the ramp. Okay, and what I see people do is they're like, okay, I got to have F net, so F net is going to be FG plus F normal plus F friction plus F parallel. Okay, and I understand why the thinking goes that way, but here's the thing you're forgetting. This is the vector sum of those two things. So you've already found the vector sum of normal force and gravity when you found F parallel. We put them tail to head right here and calculated F parallel. So they don't have to be put back in. They're already in. We find F parallel so that we can just deal with the forces that act up and down the ramp. Because in the end, those are the ones that produce the motion we're dealing with. Okay? Does that sort of make sense to everybody? Just because I see it happen a lot. People are like putting in all these extra forces and getting numbers that are way too big because they forget they've already found what Fn and Fg add up to. They've already put them in there. Okay? So F parallel takes care of Fg and Fn. Right? It's their vector sum. All right, so I got to find F parallel in this situation. Okay, I know this is 50 kilograms, so Fg is going to be 490.5 newtons. And I'm going to find F parallel by going sine of 25 times 490.5. Okay, 207.29 newtons. All right, we've now accounted for all the forces. F parallel is pulling down the ramp, force of friction is resisting up the ramp. Can I find F net? I can. F parallel plus the force of friction gives me F net. All right, so I will have F net being 207.29, and I'm just going to subtract the force of friction. I'm going to make down the ramp positive in this case. Okay. So we'll take that and we'll subtract our force of friction. All right, so there's our net force, 57.29. I can't believe how much there is. 57.29 newtons down the ramp. They want the acceleration, so I just have to divide that number by 50.
Make sure you see down.
Okay, 1.15, we only have two sig things, 1.1 meters per second squared. Downhill. This is the lamest sledding hill ever. Okay, 1.1 meters per second squared, this like snow must be like really like melty and sticky and not fun, because that's not fast at all. Alright, everyone kind of follow me on that? Okay, so the big thing we have to remember, okay, with inclined planes is we already take into account gravity and normal force when we calculate at parallel, so they're already done, don't put them in again. Okay, I've got a couple here I'd like you to work on just for the next 10-15 minutes here. Alright, they're gonna be in your digital workbook here, but they're gonna be on the forces of vector quantity page. Alright, so I would like you guys to try, let's say 3 and 4 for right now, and then we might try a third one if we have time. Okay, 3 and 4 for right now, I'll make it bigger. Okay, so 3 and 4. We did a whole bunch like number 3 yesterday, okay, those static condition examples.